Welcome to This Explainer. Today, we're unpacking a truly groundbreaking paper from Sakana AI and the University of Tokyo. We're looking at a solution to a massive hardware limit in artificial intelligence. You know, the kind of bottleneck that's literally been keeping researchers up at night. It's called diffusion blocks, and let me tell you, it fundamentally changes how we train neural networks. Here's our roadmap for This Explainer. We'll start with the AI memory bottleneck, then look at the promise of blockwise training, dive into the diffusion block solution, break down how it actually works, check out the testing architectures, and wrap up with the future of scalability. Let's get right to it. Part 1, the AI memory bottleneck and the scaling problem. Okay, so let's kick things off by confronting a bit of a paradox. We all know generative AI models are scaling incredibly fast, right? They're getting smarter, more capable, and vastly larger. But here's the catch. The hardware memory required to train them, it simply cannot keep up. It's like we're building these massive digital brains that are physically just way too big for the silicon skulls we're trying to stuff them into. The core issue here lies in standard backpropagation, which is basically the engine of modern AI training. When you train a standard neural network, end-to-end backpropagation forces the computer to memorize every single step of the network's thought process all at once. It has to store all those intermediate activations across every single layer just so it can update them later. And as these models get deeper and deeper, the memory consumption just grows linearly. It creates this enormous, completely unsustainable memory footprint. Moving on to part 2, the promise of blockwise training, along with its limitations. So this massive memory footprint brings us to an obvious theoretical hope: blockwise training. On paper, the idea is super simple. Instead of backpropagating through all those sequential layers from top to bottom, what if we just partition the network into smaller, independently trainable chunks? Well, the problem is this approach has historically failed. Past attempts relied on these ad hoc, localized objectives. They were effectively training pieces of the brain in total isolation, without any unified goal. And you guessed it, that consistently ruined the AI's overall global performance. But now we have a massive shift. In a standard network, you have this long, memory-heavy requirement of backpropagation dragging through every single layer. Diffusion blocks, on the other hand, successfully isolates these blocks. It chops the network up, sure, but thanks to a completely unique mathematical approach, it does this without losing the global picture. Each block learns independently, which drastically cuts down the memory required at any given moment. Which brings us to section 3, the diffusion block solution and its mathematical foundation. To figure out how to make this work, the researchers actually looked over at score-based diffusion models. Think about how an AI generates an image. It starts with pure chaotic static, right? And then it gradually denoises it, step by step, until a crystal clear image, like an adorable corgi puppy, finally emerges. Well, the researchers had a massive realization. They figured out they could treat a standard neural network's sequential layers as exactly this, a continuous time diffusion process. There's a specific concept from the paper that acts like a theoretical cheat code. In a diffusion model, the denoising step at a specific noise level actually doesn't need to know what's happening at the other noise levels to be optimized. By interpreting standard network connections, specifically the residual connections and transformers, as discretized steps in this continuous time diffusion process, they proved that each block can be trained entirely on its own. It's all perfectly coordinated, without needing any backpropagation between the blocks. Absolutely brilliant. Section 4, how it actually works, and applying the theory. So how do we actually do this? Converting a standard network takes 3 clean systematic steps. First, you partition the network's architecture, literally chopping the layers into independent blocks. Second, you define a noise distribution and assign a specific noise range for each chunk to learn. For example, one block might handle the really high static, while another handles the super fine details. And third, you augment each block with noise level conditioning. Basically, you add a signal so the block knows exactly which level of noise it's supposed to be cleaning up. Now, here is the paper's absolute secret sauce. You can't just slice these noise levels evenly. If you think about the learning difficulty like a bell curve, most of the really crucial, difficult learning happens right in the middle, at the intermediate noise levels. So instead of uniform spacing, they use something called equiprobability partitioning. They intelligently divide the workload by cumulative probability mass. This trick perfectly balances the difficulty across all the blocks. Narrower intervals are assigned to those super challenging intermediate noise levels, where the AI really has to do a lot of heavy lifting to figure out the structure. And then wider intervals are given to the easier extremes, like pure static or near perfect clarity. It effectively acts like a natural curriculum, ensuring that no single segment of the network ever gets overwhelmed with too much to learn. Okay, Section 5, Testing Architectures in Practical Generative AI. The results across different tasks are just stunning. Whether it's a vision transformer doing image classification, a diffusion transformer generating images, or a mask diffusion model doing text generation, Diffusion Blocks completely matches the performance of standard end-to-end training. But the real kicker is the memory cost. It does all of this while reliably using around 3 times less memory. And that's because only one block needs gradient computation at any given time. To really appreciate this achievement, we have to compare it to earlier, highly publicized attempts at blockwise training. Take Geoffrey Hinton's forward-forward algorithm, for instance. When researchers applied it to modern architectures like vision transformers, it practically collapsed, scoring a mere 7.85% accuracy. Diffusion Blocks, on that exact same task, it achieved 59.30%. That massive difference really highlights why grounding your training in the mathematical foundation of denoising score matching is so incredibly vital. It actually works on modern architectures. And the benefits just keep building. Diffusion Blocks isn't just for native diffusion models. It extends flawlessly to standard autoregressive text models, the kind that power your favorite chatbots. Plus, when applied to recurrent depth models, which normally require looping the exact same data through the network dozens of times, Diffusion Blocks converts that multiple iteration nightmare into a single clean training pass. In their tests, it eliminated up to 32 backpropagation iterations entirely. That is a massive computational saving. Finally, Section 6, the future of scalability and breaking physical limits. Because Diffusion Blocks only calculates gradients for one block at a time, your memory footprint literally shrinks proportionally to the number of blocks you partition. This is the 1/b scaling law, meaning if you take a massive, totally untrainable model and slice it into 4 blocks, it now takes roughly a quarter of the memory to train. You're getting a 4 times memory reduction without sacrificing an ounce of your output quality. With independent, blockwise training finally grounded in stable mathematics, the ceiling has completely been raised. It really forces us to wonder, what previously impossible, hyperscaled models are researchers going to build next, now that the hardware shackles of end-to-end backpropagation are finally off? This paper is a massive leap forward, and I hope this explainer helped you grasp just how elegant the Diffusion Blocks solution really is. Definitely keep an eye on this space